for the brave people that is still here in the last day. Early morning after a rainy day with a lot of traffic, so thank you very much. Now it's my pleasure to present Professor Celia Anteneodo from the Pontificia Universidade,
Pontificia Universidade Católica.
Católica. Yeah. Celia, here we don't do long introductions, so please, the word is yours.
Okay. Good morning. Thank you very much, Silvio, Marcus, and Guilherme, although they are not here, for the opportunity. So this is about, as you see, opinion dynamics. I will try to go beyond the standard approaches that are related to binary options and pairwise interactions. So I divided the presentation in 3 parts. One is about opinion dynamics beyond pairwise interactions, not in the sense of high-order interactions where there are 2, 3 or more individuals that are interacting mutually, but when we have an individual that is influenced by a group of pressure. Then I will show the case of going beyond binary choices when we have multiple choices, and in this case also there will be the pressure of a group. And if there is time, I will show a case that is related to epidemics that has the influence of the pressure of a group too. So the idea of social pressure was seen empirically from the experiments by Solomon Asch, that perhaps you know, conformity experiments, when there is, for who don't is not familiar, there is a group of individuals, actually it's focal individuals and the other are actors. So they are, a question is posed about to choose from previously given information, this card for instance, then a second card is presented with options and the first must be recognized. So individuals, the focal individual will previously listen to the responses of the actors, and depending on the size of the group and the composition, there may be some that will give an answer, others another. Depending on this composition, then the focal individual will give a response that not always is the rational one. So there is a strong tendency to go along with the rest, the pressure group. So what I'm going to model is not this situation, but to use this as a starting point to model the influence of a group. So the kind of structure we will have is a focal individual that will be influenced by all or some of the neighbors in a lattice. And for that, I will consider a family of models that are the Bottle models. In this family, many of the cases, I cannot see, there many are already developed in the literature. The basic case is the well-known Bottle model, where we pick only one of the neighbors, and there is a simple imitation of the opinion of that neighbor. Then it was presented the Q-Bottle model, where there is a group of influence, a lobby group that is selected. It may eventually coincide with all the neighbors, but in this group, all must have the opposite opinion to have a flip in opinion. So it's what we can call the unanimity model, in which all must be contrary to change the opinion of the focal one. And a more general version that we developed is the so-called threshold Q-Bottle, where we consider a group of size Q, but then the influence will be given by, dependent on not all need to have the same opinion, the contrary opinion, but it's enough that above a threshold of contrary opinions to have influence. So this is what you call Q voter. Actually, the threshold is Q0, okay? Q is the size of the group. And also, well, some particular cases, of course, if both are equal to 1, we recover the standard voter. When there are equal but not 1, you have the Q voter, the unanimity. And there are other cases that may be interesting. For instance, the 2/3 is the Byzantine majority. The Q/2 is the standard common majority. And we can have other minimal values, not necessarily majority to influence. And also, we added some noise in the dynamics to consider that the evolution was not strictly given by the influence of the group, but eventually the individual can take their own opinion independently of the group of pressure. So with certain probability that we define as P, the individual can change opinion without looking at the group. So this was initially studied with Alain, who was a postdoc, I supervised. And then we started to collaborate with a group of social dynamics in Palma de Mallorca. And so the results I will show are in collaboration with all of them. So here the question is, starting with, by considering this mechanism of social pressure, is to ask how this social pressure will affect the propagation, the social contagion, and which are the collective states that will result from these interactions. So here I'm summarizing previously what I'm going to show to you. First, I make some comparison the results obtained for the dynamics in different random networks compared to the mean field case. There is also an observation I have to do first, that is in the case where we have a mean field, if when we pick a group of certain size, we make some repetitions or not, this will not be relevant. But in the case of networks with a structure, this will give rise to different results, as I will show. So I will consider the case where the composition of the pressure group is strictly composed by different individuals, or some are repeated in some sense. This will represent a situation where there are some individuals that exert more influence than others. And also I wanted to focus on theoretical results using a pair approximation that gives results that are in good accord with simulations and seems to be adequate for these kind of models. So first, the mean field. Sorry. In the mean field, the description is easy. We have here two possibilities, yes or not, for and against. So we can consider simply the fraction of one of them. And the dynamics of diffraction is described by a simple equation where this G is the conditional probability of flip, given that the sorted agent to interact has opinion -1. So this G will be composed by the two mechanisms. We'll consider the random choice that represents the individual taking a decision independently of the group, and then with complementary probability, the flipping probability which represents the social pressure mechanism will act. And in this case, as we consider a threshold to compose this flipping probability, we'll have to add over all the possible cases, groups that are composed with individuals with the opposite opinion in number greater than Q0. So here some particular cases when Q0 and Q, the size of the group and the threshold coincide, this will become a power law. In particular, if Q is 1, we will have a linear relation between this flipping probability and the fraction of the plus opinion. So this is the linear case when Q is different from 1. We will have different power laws, but in our case, when there is a threshold, you see that we can have sigmoidal forms, different forms that allow to interpret this gene as a response function, how the individual responds to the group is given by G, and dependent on the relation, on this relation, we will have different results. So in some cases, we see that when the threshold is very high, as in this case, the threshold coincides, we have a power law. So small fractions will make the response almost insensitive. I will need to have a larger fraction to react, but you see that for intermediate values of the threshold, arriving here to, here I'm covering also the case 1 over 6 below the simple majority, we have a rapid reaction to the pressure. So what we see here, as we have this equation, is easy to analyze and to obtain analytical results. Here, what I'm showing is the two typical pictures that we have. We can have, depending on the parameters of the social pressure, we can have a continuous transition from an order to a disorder state. That is, order is one in which one of the opinions dominates and another in which they are in equal proportions. And we can also have a regime where we have this continuous transition. This can be analytically obtained, and we obtain critical points, also the intervals of the threshold values that will give rise to one kind of transition or the other. This is in the mean field. And here I'm showing a phase diagram and in the space of parameters P and Q0, where we see that this is a region where there is disorder. Here is the ordered phase, where there is dominance of one of the opinions, and this is an intermediate region where there is coexistence, that is, there is multi-stability, and dependent on the dynamics, one can end in one or another of the local minima. So this is a picture for the mean field. Then I'm showing here the case of the same dynamics, but in regular, random regular networks. And I am comparing the cases of mean field here. This line is a random regular without repetition. As I said, in the groups, we can repeat or not the certain individuals at random. Here is not allowed, and here is allowed. And the columns correspond to different values of Q, that is, the different sizes of the lobby group. And this is a main field I have just shown in the previous picture. And you see that in random regular, there is not, the picture doesn't change very strongly when we don't allow repetitions. If we allow repetition, we clearly see here that many of the discontinuous transitions disappear. So the fact of considering not repetition seems to have a stronger effect than the structure, or the random structure of the network itself. And So to obtain analytical results for the case of random networks, we consider the pair approximation, where instead of describing the dynamics in terms of the density of the species, the fraction of each one of the two species or opinions, here we consider the fraction of active links. That is, those links that join agents that have different opinions and therefore are those that can change. So we have dynamics now for this density of links. In the case of the fully connected network, the mean field, there is a relation between both. But in the general case, they are independent, and we must take equations both for the density of links and the density or fraction of one of the options. So here, in comparison to the mean field flipping probability, conditional probability, here we will have a different function that we can define for just by combinatorial analysis for the case without or with repetition. And I will not enter in details, just to illustrate the kind of equations we have. But what I want to highlight some points. For instance, one of the points is that the equation will depend mainly on the average degree over other characteristics of the network. This is in the version of the pair approximation we consider that is based only in the single degree distribution. So it will be good for cases where there is not a high clustering or strong correlations. Otherwise, we will have to extend the pair approximation to a case that will consider joint probabilities of degrees. So in the case without repetition, we managed to perform the summations that appear and obtain closed expressions, and then obtain closed expression for the critical values and for the intervals of the Q0 parameter that will give rise to the different types of phase transitions. So I wanted also to come back here to show that in this picture, actually each one of these bars has two parts, and one of them corresponds to simulations and another to the theory. So when we see that there is no discrepancy between both sides, there is a good agreement. In general, there are only, perhaps here you can see, there is some discrepancy between the two sides. So in general, it works. We can delimit in which cases it will fail, but in general, the pair approximation we are using is in good agreement with the numerical simulations. So just to illustrate, in the case of random regular, here I'm showing an example where there are the simulation, the theory, and also these dotted lines correspond to the mean field. In this case, they are very close, but there is a small discrepancy, and the pair approximation captures it, and these two colored coincide. Here is another case where you have here the mean field. In the case of the random network, there is a smaller critical point, and the simulation and pair approximation are in accord to give the critical point. You see that there is some structure here that seems to have a more multi-stability that is actually observed in simulation. So there are some spurious results in some cases. But if we are interested in determining the critical point, the pair approximation gives good results. So with repetition, we don't have closed expressions. The summations cannot be performed exactly. We have only numerical results. And what we see in the expressions, even if we cannot sum and resolve them, is that the results will not depend only on the average value, but will depend on all other moments, negative moments of the distribution of degrees. So in this case, we expect that different networks, network with different structure, but same mean will not give the same results. This happens here. I will show soon. Sorry, I haven't put here. But in agreement with the prediction of the pair approximation that the result will depend on the mean value of the degrees, then for different networks, but same average degree, we obtain similar results. So here, let me see, is the case of allowed repetitions. And I picked some cases that are in, for instance, here shows a case where the mean field predicts a discontinuous transition, and it is broken in the case of the repetitions. Also, the critical values are different. And in all cases, we have a good agreement between pair approximation and simulations, even if we don't get analytical expressions, but we obtain the solutions numerically. So here is the case. I haven't shown in the case of the without repetition, because as I said, different networks, if I plot the result for different networks, for instance, power law or Erdos-Renyi, or even random regular, the results coincide. But here, you see that it's subtle, but if we change for instance, the power law of power law networks, there is a deviation that is not observed in the case without repetition. And also, here below, I show numerical simulations. Here is the theory, numerically obtained, and there is an agreement between them. So let me summarize this part. So what we see is the structure of the group, defined mainly by the ratio between the threshold Q0 and the size of the influence group Q, has a strong influence on the results. It determines the transitions, is more influent than the structure of the network itself. So as I'm summarizing what I have already said, in the case of without repetitions, the network structure influence only through the average degree. And with repetitions, we see that discontinuous transitions tend to disappear, are less common, as in the case of the random regular that I shown at the beginning. And also, there is disagreement between networks with different structure due to the influence of the moments different from the mean that are typically negative moments. And with respect to the connection with the theory, as we have seen, there is in general good agreement, except in some cases that the theory gives some spurious results. And let me see if there is something else I wanted to comment. These are technical details. I will not comment about the performance of the pair approximation, but who is interested, I comment later. So this is the, I want to pass to other part where we study the case of multiple choices. This was done in collaboration with former students and postdocs that now are professors at different universities. So the motivation here is to go beyond the case of choices between yes or not, or for or against, and face situations where we have multiple choices that may be serious choices, like which is the career a student will follow, or just to buy some simple product in the supermarket. Here I illustrated with the case of shoes that I have that problem buying these shoes. For me, are all equal. The prices are similar. The colors sometimes are also similar. There are subtle differences. There are not a preference for one of them. So there have the characteristic, in the case I might consider, is that there is not a particular attractiveness. They are all similar. Of course, the problem will be different if we have a rank of preferences. So on one side, to have these many alternatives is good, to have a diversity of options, but on the other, there is the difficulty that the process of choosing becomes more complex and can lead to a phenomenon that is known as overchoice. That is, there are so many possibilities that are equal that individual ends by being undecided and don't buying anything. So of course there is complex psychological features involved. It's a stressful task to make these kind of decisions, but we are going to see how the interactions can contribute to this kind of phenomenon. And also the case of many options may be interesting to see the phenomenon of varialization, for instance, how being all equally attractive, the options, one can emerge as a dominant one. So this is the motivation, and to deal with this situation, we consider a model based on the so-called plurality rule. The agents can take, the state variable that defines the opinion of the agents can take here also Q values, the equally attractive alternatives. And we also consider an undecided state, okay? So in this plurality rule, the influence will be given by that opinion that is the dominant one. So will adopt the opinion shared by the largest number of nearest neighbors. As illustrated in this picture here, the red has two representatives. Here, this has also two, but is the undefined state, and this state will not count for the social pressure. And so this red will be the opinion that will influence the focal subject, okay? If in the case that there are several, that there are ties, in this case we do nothing, okay? So I want to comment that this plurality rule, I don't know if with that name was previously proposed by Chen and Redner, but in the model they considered they were not undecided. And for our questions, it was important to incorporate the undecided state. So here I show the kind of the typical patterns that can appear. Here I represented the number of adopters of each one of the options. Here are 20 options, so all are represented, and as a function of time. And you see that this ends in an absorbing state where, in this case, the green is the undecided dominates. You see that there are options with a certain number of adopters, and there is a winner one, but it's not too far from the others. It's not a clearly dominant one. There may be also the case where, as in this case, you see that there are other options. In this case, there is clearly a dominant winner. Here, the dominant winner becomes unanimity, is a case of consensus. In this case, you see that the undecided remain, but are at a low level. In this case, they disappeared. And an extreme of this first situation, the dynamics based when the number of alternatives is too high, as in this case, 150, the dynamics is frozen from the start. I didn't comment, but they were considered the case where the starting, the initial state, all are undecided except some initiators of each one of the options. This is the initial state we're considering.
Talk of Professor Celia.
Okay, let's end. So I had just shown you the typical patterns that can happen in different networks. And I want to comment now what happens in each type of network. In the mean field case, where we have a fully connected network, but actually we don't pick everybody. We pick groups of a certain size so that we can compare with other networks with a given average degree. So, but in the case of the mean field, here I don't know which is the K in this case, but in any case, what we see is that a consensus is reached when the interactions are mean field. Also analytically, we can see that. In other networks, like in the regular square lattice, we already see some behaviors that resemble those that I illustrated as typical ones. But in this case, the dynamics is rather trivial, because what happens is that there is actually a non-interacting phase. Each initiator will grow its preference around until these groups collide. In the interfaces, we will have undecided guys, and this will end there. So it's rather trivial in that sense. But in other networks, Erdős-Rényi and Barabasi-Albert, we see really different kind of behaviors depending on the average connectivity and the number of options. Here, for instance, for Q, that is the number of alternatives equal to 20, we see different behaviors. For instance, here there is a wide distribution of opinions and the undecided wins. Here they are undecided false, but we see that there is a separated winner from the rest of the distribution, like an outlier if we represent the distribution of opinions. And also consensus in some cases can be reached. Okay, and if we increase the number of options, we see that the undecided take a larger proportion of the population, and also in this case, a consensus is reached. But consensus is reached only when we have a high connectivity, tending in some sense to a mean field case. Here I am showing a comparison for K equal 4 of the different networks, Erdős-Rényi, Barabasi-Albert, the square, and the mean field. And you see that the Erdős-Rényi, that is not heterogeneous, has some resemblance with the square, not for the same K. Of course, a different K will produce a better matching, but I'm showing qualitatively the kind of behavior where in this case, there is a dominance of the undecided opinion, and while we see this correspondence with those that have regular behavior, the Barabasi and mean field have some resemblance in which, in the sense that it tends to reach consensus, and in some cases there is consensus. So here I showed a phase diagram for Erdős-Rényi and Barabasi-Albert, where we see here we performed many realization and monitored the fraction that reached consensus, that is represented by this color bar from 0 to 1. And you see that this is a region that most of the cases reaches consensus. Here too, But here is different. But Bassi-Albert, below a certain connectivity, you see that consensus is not always reached. Also, this is the line for the winner equal to 0.5. And in this case, we see that even for larger connectivities, we not always have consensus. If the number of options is very large, there will not be consensus anymore. And here is a shadowed region that is a region that represents when the undecided opinion wins, when it's, or at least when it is larger than 1/2. So the network structure influences, but in both cases, I will say here there is a transition. In this case, it seems more abrupt, and we study this analytically now. But what we see is that if we decrease the number of options or increase the number of connections, we can have a transition to consensus, what will mean a dominant winner. And well, this I think is the main conclusion here. And what we have done here is try to validate the model with some empirical. Let me comment first that what we have done is to look at the distribution. As you see here, there is a distribution of opinion, and in different points of these diagrams, we look at the distribution, and what we see is that it can be, in the case of Erdos-Renyi, in this region, it can be exponential. Closer to this frontier, to consensus, it becomes log normal. In the case of Barabasi-Albert, I'm not showing here, it is typically log normal. And coming close to the frontier, some power law tails develop. Here I'm showing for the case of Erdos-Renyi some cases with different K. This, you see that is a log linear plot. These are exponential, and this was fitted by a log normal. So these are the typical distribution we see in this model. So we wanted to compare this with some empirical data, and then we picked data from the NetShows site. We also picked the Google Play Music that doesn't exist anymore, but at that time we have these musics. So you use the ratings as an indicator of the adoption of each one of the alternatives. Okay, so these are the two products. Also, this has a fixed had at that time, almost fixed price. That was $9 or about. And the shows have more dispersion, so we consider two subsets with below and above a certain value. So we identified Q with the number of items, that are the number of alternatives to choose, and then the number of adopters of each one of the cases we associated with those ratings that were with 4 or 5 stars, that is a maximum. And then this is the kind of distribution we see in both cases. Here is the both subpopulations are here. The two cases, low and high price, and they're surprisingly coincide. And here also, in both cases, we performed log normal fits. So in some sense, we were surprised that this statistical behavior coincides with the prediction of the model, even if the model is rather rudimentary. And we try to extract some information about the network, but in both cases, we analyzed Erdos-Renyi and Barabasi-Albert. In both log normal can arise. So what we can say is if it is close or far from the frontier to consensus, for instance, but not to identify the structure, because the log normal seems to be common of the even very heterogeneous or more homogeneous networks. So what I want to highlight to finish is that this plurality dynamics that we applied to the scenarios where there are homogeneous options through this model, we have seen the emergence of different states, consensus, broad distribution of opinions, The phenomenon of overchoice also emerges. The viralization also emerges. So we see with the model phenomena and try to validate the distribution we observe in different regions, comparing with real data. Perhaps this can be improved, but at least what we have done shows a certain consistency. There was a third subject I wanted to develop, but as there is no more time, I just wanted to make the publicity of this work. Perhaps many of you know, because I want to mention it was with Silvio and also Diogo. That is about epidemic outbreaks with adaptive prevention. We were asking about if the adoption of some prophylactic attitude like using masks or other, in what measure it will affect the prevalence of the disease, and also try to see how if the adoption is influenced by the knowledge or awareness about the situation from local information, the neighbors, or from global information. So this is what the paper is about, and we conclude that the local information is obviously more relevant. Okay, this is what I wanted to show, and that is all.
Okay, thank you, Celia, for the lecture and also for my picture. Thank you. And we still have time for questions because I discount the time when the energy was out. Please, Hugo.
Hi, Professor. Thank you so much for the talk. Could you return to the overchoice model? I wanted to understand when it ties, for example, you have two options that the neighbors have the same numbers. What do you do when the tie occurs?
Nothing.
Nothing happens.
Nothing.
Okay.
Yes, I know that we are going to model this analytically. It will be one of the tasks is to include these effects. For instance, to choose one of them at random, for instance, instead of doing nothing.
Okay.
And other variants. Okay? But at the moment, we have not analyzed that case.
Oh, okay, because I was going to ask, because I was thinking if it makes any sense, maybe it doesn't make any sense. Because if I have too many options, maybe I would go to the undecided if my neighbors are
Yes. In this case, we don't go to the undecided, but it is also interesting to include that possibility too.
Okay,
yes.
okay, yeah. No, thank you so much.
Yes. In the case of ties, for instance, it could be precisely.
Okay, since no one has, I have a question. May I? Oh, sorry, Andre.
I will just compliment what he said. If you change to choosing one of the random majority ones, I think the only absorbent state is going to be consensus, right?
In which case?
If you go to, in the situation where you have a tie, for example, you choose one of the largest
instead
ones
of
at random.
Instead of doing nothing.
Yeah, I think the only absorbent state is going to be consensus in this case, right?
Maybe.
Celia, thank you for your talk. I was wondering about the comparison with the data.
Sí.
I don't know why it fits. I mean,
why what?
Why the data agree with your model? Because I don't understand why the dynamic.
We were surprised too.
Yes, but you think that there's some hidden mechanism there that it could be your model is relevant to this kind of feature because this is a very common distribution and by chance you
I don't know because really this study was rather limited and we are trying to extend it with analytical approach to cover other citations as is commented here. So we don't know if this is robust or dependent of the model. No?
Yeah, Celia, thank you for talking. Nice. The I want to comment about this dissonance when you have a similar choices from the point of view of the brain. What happens usually is that, have done this even in animals and in humans, in experiments, that if you give the same bad choice or the same good choice, meaning you put the animal to choose between good food and good food, or a shock and another stronger shock, and there is no difference, your cortisol, your stress goes up. Because evolutionary, the brain is prepared to choose between good and bad. But you have too much money, you don't know what to do. I don't know what to dress for tonight. And it produces stress. So that stress frozen the decision. So in decision making, there are strategies to break that tie. So I don't know if it has anything to do with your result, but this is something that is well done in behavioral neuroscience. And I'm wondering if that can be modeled or not. I don't know, it triggers some thinking on you, but thank you in any way.
Yes, okay, thank you. Perhaps there is a way to include it. And I commented that, of course, there is psychological factors that are not being considered here, but it's well known. I know that overchoice is a phenomenon well studied. But we wanted to see up to what measure this predominance of indecision can come only from interactions, independently of a psychological factor. Okay. Perhaps in the rule, in the effect of the social pressure rule, it may be incorporated.
Okay, I do my question during the coffee break, so let's thank Celia again.
Okay. And yes, sorry, I was wondering about your question, and I think that, yes, it will go to consensus. Yes.